Perfect, and everyone can hear me. So, hi everyone, my name is Devyani McLaren. I'm a PhD student presenting alongside fellow co-author Jian Gao, another PhD student from the University of British Columbia. Today we're going to tell you about our novel capacitive touch sensor array and what it has already helped us learn about affective social touch. Affective touch is a fundamental form of nonverbal human communication, and there's evidence that our hand movements are expressive of our emotional state, particularly when that emotion is very intense. Now, HCI applications that can capture and interpret these signals would have a pathway to be emotionally intelligent in a very unobtrusive way. But trying to design for this innate touch emotion connection is a bit hard since we don't have precise requirements. Human skin is certainly a good place to start, given that it has the highly specialized mechanoreceptors that detect different frequency ranges, different types of forces, slip, sideways shear, normal pressure, and many more. Now, current sensors that have been developed typically only focus on normal pressure. Our focus was to add shear sensing capability to normal stress as well, and to get a first impression of the importance of these two modalities in distinguishing key properties of different emotive gestures. We also needed a package that was soft and flexible and could be laid over devices that could elicit emotionally expressive touch. Now, these devices tend to be quite soft and squishy. We initiated this project by analyzing affective touch gesture properties. And from these properties, we synthesized important sensor requirements, and we carefully chose a test set of 9 gestures to fully test the capability of our sensor. We reviewed psychophysics and sensor design literature to estimate relevant ranges and requirements for our sensor, and this process resulted in touch properties mapped to sensor requirements, further mapped to test gesture definitions. Essentially, what we learned is that our sensor needs to be able to capture variation in different properties like stress angle, contact area, modulation, forcefulness, and much more. Through this process, we extensively characterized the sensor, collected a large amount of touch data, and developed machine learning models to detect gestures. Throughout this process, we had to constantly juggle different considerations for affective touch properties, our sensor design, and our machine learning modeling pipeline.
Great, thanks Devyani. So let's dive into the sensor part of our presentation. So here's a quick look at our 3-axis capacitive stress sensor, including, let me turn on the laser pointer. So including the top transmission electrode, which is labeled as the TX electrode here, and also 5 receiver electrodes labeled as RXs. So if we apply a normal stress on the top, and we can see this increase in all the 5 capacitive channels. And we can evaluate this displacement in the normal direction according to one of the capacitance changes, which is the C3. And on top of the normal stress that we applied, we can further add shear stresses, leading to this imbalanced changes in C2 and C4. So from those 2 readings, we can get the shear measurement along the x-axis. Same applies to another shear axis, which is along the axis of channel 1 and channel 5, so for C1 and C5. So we use this example to build a lot of sensors already, actually, so we can find some papers that are quite interesting, ranging from healthcare, industrial application, normal HCI interfaces, and also robotics. However, we know that the previous sensors, they don't provide good enough quality or good enough sensitivity for the affective touch, especially given the context that we might be able to apply the soft sensor to some soft backing. So how can we deal with this problem? We really focused on the pillar layer. So here are the 2 things that we did. So the first thing is we changed the previous cubic shape for the pillars to this now inverted truncated pyramid, inspired by the work by Zelan Bao's group at Stanford back in 2010. The second thing we did was to change the previously adopted EcoFlex 30 or EcoFlex 20 to this EcoFlex gel, which is the softest material in the EcoFlex lineup, provided by the company Smoothon. For the rest of the layers, we keep it all the same, including the flexible PCB layer at the bottom, the conductive fabric layer as the transmission electrode, and also the top elastomer cover layer. Now let's talk about the assembly of our sensor. So here we have this 3-step modeling process just to get this structure right, including the TX electrodes embedded inside of the elastomer. And then we send our design to a PCB factory so that they can make the flexible PCB for us. And after that, we can just combine these two different structures together to make an entity. And in order to do that, we adopted 2 adhesives. The first one is a non-conductive adhesive, SS6000. The second one is conductive adhesive, SX26, both from silicon solutions. And here, the whole structure comes together. And this is how it looks like in real life. So great news for the graduate students, because it only takes 2 hours for a graduate student to train an undergrad to do this, but too sad for the undergrad students, because it takes 4 hours for them to make one. So yeah, maybe 2 sensors per day. Not bad, not bad. All done in the lab. And now the sensor is ready to be connected to the external microcontroller for data readout. Again, here's a look at the sensor. We want to connect it to a custom miniaturized microcontroller that we developed in the lab, which has only 4 millimeter of thickness, very compact, and low power. So this is connected by a FPC connection. And then the microcontroller obtains all the capacitive readings and sends out all the data through a wireless Bluetooth connection to a nearby Windows PC through a dongle. And the Windows PC is using Python to parse all that data for data visualization and collection. Now we talk about the modeling or the user study of our paper. So here's a quick look at the data collection. So we conducted the first block for each individual, which contains 13 sets of 9 different gestures. Then we proceed so for another 3 blocks, leading to a total number of 468 gestures collected. Then we do the same for the rest of the group, including another 15 participants, leading to a total number of more than 7,000 gestures collected. Then we run the whole data chain through this pre-processing pipeline, for which further details can be found in the paper. So we split the data into 2-second chunks and feed them into this custom 3D CNN structure, which has 3 convolutional layers and 1 output layer that gives out the probability vector. Here are 2 sort of modeling that we did using this data repository. So first one, we just used all the data instances to do the training, validation, and also testing. And here's a confusion matrix for the different 9 gestures. You can see the top 3 performers here are the white pinch, circular stroke, and constant. It's interesting for the constant, you can see there's only a few misinterpretation towards twist for this specific gesture, so it's actually recognizing it very reliably. So this is done using all the 3-axis information. If we compare this model to a normal force only or shear force only model, you can see the advantage here actually. So let's take constant again, for example. We have 99% of accuracy using the 3-axis model, while the normal and shear models only have 76 and 94% of accuracies. And this is true for most of the gestures, but there are definitely outliers. For example, for poke, the shear has the best performance. So this might be like a separate study on its own, but in this paper, we really only focus on the high-level picture. So in general, the 3-axis model just does better if we just take the average of all the different gestures. So here you can see, for the median accuracy among all gestures, the 3-axis model has the best performance, ranging around 88% of accuracy, while the other 2 models are just like hovering around 80%. So here's the second test that we did. So in this, as a bit of context, we were like, hey, what if we take our system and our trained model to a total stranger to a system? Can our system still do the gesture classification effectively enough? In this case, we divided our data repository into 2 parts. This first part contains the 15 participants' data for training and validation, while reserving the last participant data for testing. So in this graph, the x-axis has all the labels of the participants being left out of training. Here are the top two performers, PA, P14, pretty good results. However, they are just like people who are just performing gestures slightly differently. In this case, personalized model might be needed in our future.
So overall, our research highlights the importance of Shear in affective touch and introduces a novel sensor which we've demonstrated can capture this complexity. Detailed characterization of touch gestures enables a system like a therapeutic robot to perceive human touch for more authentic and comforting interactions, and we've gained valuable insights through machine learning. And we also provide design guidelines for future projects that may be inspired by ours. In the future, we are looking at a careful process of testing the sensor in genuinely emotive contexts, while refining its sensitivity, scalability, and form factors. Now that we have a platform that can be used to estimate affective state, and since this sensor is flexible, we can start integrating it into soft social robotics. Thank you so much for your attention. We saw many of you at the demo, and I see many familiar faces, and we're happy to take any questions.
Hi, Wujay Chang from UMD. Thank you for the talk. I was just wondering for gesture categorization, if you drew from like existing literature of any existing frameworks,
Yes.
and if you compare them with other frameworks to see if if any of them like particularly mapped out better than the other ones.
So are you talking about the models that we adopted, or just like the sensor side of
So
it?
when you're categorizing different touch, like poke, circular motions and stuff. So those types of different touches. How did you come up with individualized selection?
So from our lab, we have some work called an affective touch gesture dictionary, and that's where we drew inspiration for a lot of the gestures that we chose. However, what we did is we further took those gestures and applied them and saw what their relevance to affective touch was through the affective properties that we'd already previously created for this project. Now, to give you an example, I can actually throw up the table. So these were the gestures, and in the paper itself, we cite the specific papers of where some of these gestures came from, and we also state which gestures were new that we added because we felt that there was a certain area of the sensor that maybe wasn't being tested. So I hope that answers your question. With regards to comparing it to other machine learning models, we don't do a direct comparison in the paper, but we do discuss how our accuracy might be slightly better or worse than other papers that have previously published things.
Sure. All right, thank you for the answer.
Thank you for your question.
Hi, thanks for a great talk. I'm Jotaro from Sony, and I have a question, really quick question about what do you think about the change in the way you touch on the on this device or many other devices that you can think of from the if there's any feedback from the object that you touch.
Currently, we don't have any actuation provided on this top surface of the sensor, but that's definitely one of the future work direction for sure.
Also some visual feedback from the object, because I saw that the image that you're touching on the pad.
Mm-hmm. Yeah, I think there are just two approaches to it. The first one is to provide the physical colors on top of the existing sensor, maybe using some electrochromic materials. So that's something we used to do in the lab. But that can have some latency. But the second approach I was thinking about is to use AR technologies just to overlay another layer of virtual display on top of it. Maybe using like a cell phone screen, or maybe just a VR headset, something like that. Yeah.
We also brought our sensors here today, so if you come to the poster session, you can touch it to feel what the haptic qualities of the
Happy
sensor
to. Thank you very much.
Yep. Thank you for your question.
That's great. Then please enjoy the poster and demo session after this, and thank you for your talk.
Thank you.
Thank you.